some of your previous math classes, I know that you went over what are called the rules of exponents or exponent properties. Specifically, in a lot of these classes, you probably learned them as the mad spam rules. I'm going to go ahead and write that before I finish this thought. You probably learned MADSPM. Does that sound any sort of familiar to you? Mad spam. Yeah. The mad spam rules are the ways that we can combine different bases together when they're the same base and have exponents. Those product, quotient, and power properties are as follows. If you are multiplying bases together, you can add the exponents. This one is not printed on your paper because I'm not going to use it in class today, but if you are dividing the bases, you can subtract the exponents. If you have a power raised to a power, you can multiply the exponents. So for example, x to the 5th times x to the 5th is x to the 5 plus 3, which is 8. 2 to the x times 2 to the 3rd, since those bases are the same, just add the exponents. 2 to the x plus 3. Do we follow? That is called the product property of exponents. If you multiply, you add. There is the division, the quotient property, again, not printed on the paper. Divide means subtract. We have another property that is called the power property. In the power property, if we have a power raised to a power, we multiply. So, x to the 5th raised to the 3rd power is x to the 5 times 3, or x to the 15, which means 2 to the x raised to the 3rd power is 2 to the 3x power. Do we follow? Okay, the next exponent property is not in the acronym for mad spam, but it's called the negative exponent property. And the way you were probably told of this property back in the day is that we don't like to see negative exponents. I still agree with that statement. So we want to clean them up by taking any negative exponent and moving it to the bottom. So if you have b to the negative n, you can clean that up by putting the b to the n in the denominator. And if your numerator is empty, you put a 1 there. So for example, if you have x to the negative 3rd power, that's 1 over x cubed. If you have 2 to the negative x power, that's 1 over x, 2 to the x. So we see how we just move it down. It's called the negative exponent property. The last exponent property you might not have seen in this exact way. It's called the rational exponent property. And if you have a fraction in your exponent, not dividing the bases, but if you have a fraction in your exponent, that actually becomes the index of your root. So 1 over k as the exponent is the kth root of b. This will make sense why, when those of you on the Gim kit we played just before this asked me 16 to the 1/2, and I said, oh, that's just square root. 4. Right? Because if it's 16 to the 1/2, that's 2 as the index of the root. That's a square root. So x to the 1/2 power is square root x. 2 to the 1/3 power is cube root of 2. Whatever that denominator of the power is, that's the index of the root. Make sense? Okay, so those exponent properties we've been seeing since forever, so we're not actually spending a lot of time just like making up cute problems about exponent properties. What we're actually going to be doing is tying this into the idea we had from topic 1.12, which was transformations of functions in general. So what I would like for us to do is review for a second how we talk about transformations, specifically the horizontal transformations from lesson 1.12. If you have your notes readily available and want to see both at the same time, there's a beautiful table we have from 1.12 you can look at. But what I want us to do is determine the transformations for each of the following exponential functions from the parent function with that base. So for example, what we would write for letter A is that f of x being 4 to the x plus 2 would be that the original function 4 to the x has been horizontally translated 2 units to the left. Are y'all okay with me using HT for horizontal translation? Because those are really long words and I don't feel like writing them all that time. Horizontal translation. That means we've scooted it from side to side. Why did I say to the left? As just like a bonus question right here. Always the inverse. Yeah, inside is the opposite of what you think, and since plus normally goes to the right, this goes to the left. Very good. We're going to leave that for right now. If we look at B, right now, how does 2 to the 3x compare to the parent function 2 to the x? What have I done? You don't have to use fancy math words. What's the difference between what I wrote and what was printed on the paper? I took off the 3, which means our g of x function is the basic function 2 of x that has been horizontally dilated by a factor of 1/3. Whoa. Where'd the 1/3 come from?
Move it down.
Again, inside is the opposite, even though it's not opposite. This is the reciprocal. So the reciprocal of 3 is 1/3. Do we see how I got these things? This is just a review from 1.12. So you guys are in charge now. Let's look at letter C. For h of x, if I'm comparing 9 to the x divided by 2 compared to 9 to the x, what has happened up in that exponent? I see what you're saying, yes. The 1/2 is there now, yeah? Or the divide by 2. So 9 to the x power has been horizontally dilated by a factor of 2 this time, because 1/2, the reciprocal is 2. How about this last one? If we compare 5 to the x minus 1 compared to its parent function 5 to the x, what has happened here? It's going right by 1. So we say it has been horizontally translated 1 unit to the right. All this is looking at these horizontal transformations that we've applied to these functions using our vocabulary from 1.12. Let's tie in some vocabulary from maybe our last couple classes. Specifically, last class we learned about exponential functions that have an initial value and a base. For this function right here, I went back to A. What is the base of this exponential? 4. If I ask you what is the initial value, you're looking for the number in front of that base. Is there a number in front of that base? No. So what number is sneaky and is there? 1. The invisible number 1. Nice. Okay, so that means the initial value is 1 and the base is 4. What's the initial value and the base for g of x? 1 and 2. What's the initial value and the base for c? 1 and 9. And then finally, what's the initial value of k of x? 1 and 5. Interesting. So the question I just got was, if there was a number there for the initial value, what would it look like? It would look something like this. Maybe we have 3 times 5 to the x minus 1. What would be initial value then? 3. Great question. Okay, so let's tie this together. Let's tie together our properties of exponents that we just went over, and then the idea of these horizontal transformations. In fact, what we're going to do is we're going to manipulate these equations using the properties of exponents to write them in an equivalent form that does not have any sort of horizontal translation. And what's really cool about this is that we can use the product property, which is the multiply add property, to show that every horizontal translation of an exponential function is equivalent to a vertical dilation of the exponential function. It changes the initial value of the function, which is pretty cool. We can also use the power property, which is the power to a power means multiply, to show that every horizontal dilation of an exponential function is actually a change of base for that exponential function. So what I'm wanting us to do is manipulate these equations into different equivalent forms so we can see the different properties when we look at it compared to a horizontal transformation versus a vertical transformation, because they can go back and forth. So what I want us to do when we see these sorts of problems is I want us to use the properties backwards from how they're written on your paper. On your paper, do you see that the product property is the one that has an exponent that says m plus n? If we go backwards, that means I can separate these two things by multiplication. So 4 to the x plus 2 can be 4 to the x times 4 to the 2. If we have multiplying, we are adding the exponents. So if we're adding the exponents, we're just multiplying the bases. See how I just kind of like pulled them apart like that? Well, now my spidey sense is kicked in here. I have 4 to the second power. What is 4 to the second power? 16. So if I rewrote this in the form I'm used to seeing, this would be 16 times 4 to the x power. We've changed it and we've manipulated it. It is an equivalent expression. It would graph the exact same, except now instead of saying that it is a horizontal translation 2 units left, we can say that this particular function is for the x that has been vertically dilated by a factor of 16.
How come we don't multiply it all?
The 4 has a power, so it's like protected. It can't multiply 16 times 4 because the base is 4 and it can't be multiplied by anything else. That was a good question. If I go further to this one, what is the initial value of this new function? 16. What is the base? 4. Interesting. They're the same exact function. I can represent them in 2 different ways. Let's do the next one. Okay, this time I have multiplication up in my exponent. This is the one where I'm going to use the power property to separate this. If I'm multiplying in my exponents, that means I had a power raised to a power. Power to a power means multiply, so multiply means power to a power. Okay, again, I see 2 to the third power. Don't say 6. What is 2 to the third power? 8, which means this whole thing can change to 8 to the x power. Whoa. 2 to the 3x power is the same as 8 to the x power? That's so interesting, and what that means is that now our original parent function, 2 to the x, has been change of base to 8 to the x power. That's the transformation we've applied. We've changed the entire base that we're multiplying by.
So the base is allowed to change?
This is the only time, great point, this is the only time your base is allowed to change. I've said that a lot, probably in the last few days, the base never changes, and you'll keep hearing me say that when we get into logarithms.
And I have to remember to write all these.
No, it'll usually come from a multiple choice question. Now if we look at this one that we just changed, so I'm looking at this 8 to the x, what is the initial value? 1. What is the base? And if we compare that to what we answered earlier, did we change the initial value at all for this function? No, we literally just changed the base. Okay, let's try C. Now for C, we still said this was a horizontal dilation. We said it's a horizontal dilation by 1/2, which means what we can do is we can separate this into 9 to the 1/2 power raised to the x power. In question B, it was very easy for us to do 2 to the third power. Can we do 9 to the 1/2 power?
Yes.
Yeah, because 1/2 power means that I'm doing the what of 9? The square root, the second root, which yes, we would just call a square root. So this is the square root of 9, which yes, you're right, is just 3. So the transformation we've applied here from the parent function, we had 9 to the x power and we changed the base to 3 to the x. What is the new initial value? 1. So it's the same initial value. What's the base? Nice. Uh-huh. Yes. Yes. Last question here. This time we're not multiplying. We are subtracting in the exponents. Now I know that I wrote divide means subtract. So you're like subtract means divide. I hear you. I wrote MathSpan up there so you remembered where this was coming from. I still want us to separate this with multiplication. Meaning we're going to separate this into 5 to the x times 5 to the negative 1. So if you have a horizontal translation, you can separate it using multiplication with two separate bases. Yes?
Why are we switching the negative symbol?
What do you mean?
Earlier you switched the negative to a positive.
By doing what? Because you're making a great point. That's what I'm going to do next. I do see that I have a negative exponent, and I don't like to leave negative exponents in my answer. So what does the purple negative exponent rule tell us to do with those negative exponents? I think I heard someone say drop it down. And I heard it. Somebody did say that. And yes, you would move it down to the bottom and change the exponent to positive. Do I need to write a positive 1 exponent? I can, but I don't need to. So here we have this, and if we write it in the form we're used to seeing, this is 1/5 times 5 to the x power. Which means that we have taken what was originally a horizontal translation to the right one, and we have changed it so that 5x now has been vertically dilated by a factor of 1/5. In which case, what is the new initial value? And what's the base? So sometimes you'll be changing the base, sometimes you'll be changing the initial value. But either way, we can take inside transformations and rewrite them as outside transformations. How do we feel?
Good.
Okay. What we're going to do to practice, because if you notice, there's no back to these notes. I've taken all of the practice problems involved with these notes and I put them on the whiteboards. So I'm going to send you to the whiteboards now. You're going to work as groups to get through. The first couple levels are free response, and the next levels after that are all multiple choice questions, which will be more like what you would see in a test or a quiz in this class. Okay?